of you have already tuned in yesterday and on Tuesday, so I don't really need to introduce Lexing any further, but today he's going to talk about Sobolev regularization of stochastic gradient descent for neural networks, which I'm very much looking forward to. So yeah, it's my pleasure. The stage is yours, Lexing.
Thank you, Martin, for the nice introduction. Okay, so today I'm going to talk about some recent work. The title is the Sobolev regularization of SGD for neural networks, and this is joint work with Chalma at also at the Stanford University. Okay, all right. So so here we consider a very standard setup in neural network. So let's assume that our data X input data is X dimensional, and the data was given as Xi and Yi. So Yi is a real number. And so this is a regression problem, and you want to train a neural network to fit this data. And the neural network has a certain architecture. It's just a feed-forward multi-layer neural network. So all the parameters are collectively denoted by W, but what it does is that given the input X, it's gonna multiply with a matrix W on top of it. So matrix times vector give a vector. And then you do activation function, for example, like ReLU, to apply to every entry of this vector, so you get a new vector. So this is the vector. And then apply W2, you get another vector, put an activation omega, well, so you end up with another vector, and you keep doing that until at the last level, you apply WAL plus 1, the last layer of neural network weights, and you get your result. And so this function, in the rest of the talk, I will call the model function. Okay, the model function has the input X, which is my data, and also the neural network weights. Now the loss function is trying to minimize this loss function over all the possible weights, and where the model function for that given weights fit the data well. Okay, and okay, so here just average over all the possible data. Now I assume that my data is of dimension D, so this is already assumed here, and the total number of neural network weights is W, lowercase w. So therefore, the capital W, the collection of all the weights, is a vector in W-dimensional space. Now we assume that we are in the so-called over-parameterization regime, meaning that we have more parameters than data, so that the neural network can fit the data perfectly. Okay, so this obviously this is an assumption, but this assumption has been corroborated by numerical evidence from various kind of experiments showing that at the solution, there exists solutions like W star, such that my training loss is 0. Okay. Now, so we're working in the over-parameterization regime. Okay. Now, what people observe in practice is that when you train neural network with stochastic gradient descent, and SGD stands for stochastic gradient descent, it gives you a very good result. Not only it brings you bring the loss of the neural network to 0, so the W star is 0. It also has something called very good generalization power, meaning that when you apply to new data, you also get the error to be very, very small. Yeah. Now, the question that we're trying to answer is that why does SGD generalize well? Okay, so and this in the literature, this is called something called implicit regularization of SGD. And one typical and probably one most well accepted explanation, put a quote as you see why, is that SGD tends to find something called the local flat minimum. Okay, so because SGD is optimization in W, so you want to find a flat minimum in W. And then a flat minimum in W give you gross generalization error. But I want to say that, I mean, because so we're trying to do some math about neural network, and this quote explanation is not very satisfactory, because really it just turned into one question into two questions. Because the first question becomes now, why does SGD find the flat minimum in W, right? So you have to answer this question. This is question 1. Now the question 2 is that the why flatness in W give you good generalization error. Well, that's not trivial, because flatness in minimum is a statement about the weights, right, in W variable. but good generalization is about in the X variable. So therefore, you're really talking about the properties for two different variables, and it's not clear how to transform them. So in this talk, what I want to do is that I want to give you like a slightly more mathematical explanation about what's going on here. So in fact, what the flatness means is that I will show you is that it really means that the gradient in W at at the solution W star is small. So flatness means that the W gradient is small of my model function. And the good generalization, at least one way to explain good generalization is that the X gradient of my model function at W star is small. Okay. So again, what we have done here is made question 1 and question 2 more precise, because we get rid of these words like flatness, generalization, which can have different meanings, but we replace them with much more precise statements about the bound on the W derivative and the bound on the X derivative. As I will show you is that the answer for question 1 really rely on the stability of SGD. So to give a slightly more precise statement, what we prove here is that if SGD find the W star in a stable way, which I will define, and then the W gradient at the W star will be small. The W gradient of the model function W star will be small. Now to answer the second question, as you will see, what plays a big role is the multiplicative structure of the neural network. Okay, so what it shows is that if your model function, as we explained here, has a so-called multiplicative structure, which I will be made more precise in the next slide, and then I can transform the bound on the W derivative to the bound on the X derivative. And once I have the bound on X derivative, by adding a little bit technical conditions about the data set, which I will explain and also in detail, is that this implies generalization, in the sense that when you apply the model function with W star parameter to a new data set, and this will give you small error as well. Okay, so this is the overall plan, and I will try to make these two questions more precise and also answer these two questions. Okay. Now what I will do here is that I will do it in a slightly reversed order. So I will explain question 2 and answer question 2 first. So let me remind you, the question 2 is that why a small W gradient of my model function at the W star implies that the small gradient in X, the input variable at W star. Now, here I'll explain what do I mean by multiplicative structure. So in fact, the multiplicativity structure of the neural network really just means that that all the parameters are multiplied with the input rather than in some other form. So you could imagine that you add the parameters to the neural network without any multiplication, or you do some, or you treat it in a much more complicated way. But the first thing you do is a multiplication is the key here. Now, in order to, in fact, this slides essentially explain the main idea. In order to explain it, it's useful to introduce some intermediate variables. So for example, what I'm going to do is I'm going to introduce a variable called H1. So H1, this is H1. H1 is activation function sigma applied to W1X. Now this is called the data. This is called the data at the first hidden layer. And now you can also do the same thing. So you take the data at the L minus 1 hidden layer and you multiply the WL matrix on top of it and then apply activation function. And this gives you the data at the L's hidden layer. So you repeat this process until you get the last layer. And at the last layer, you have the last set of neural network weights multiply with the last hidden layer, and that will give you the model function. Now, this multiplicativity structure is actually gonna be very useful here. The reason is that it makes a calculation of the gradient very easy, very transparent. So for example, if you want to calculate the gradient of this model function with respect to the weights at the first layer, this W1, And then by the so-called chain rule, what you need to do is you take the gradient respect to all the hidden layers and so on and so forth, right? So you're gonna take what here is the gradient respect to the first hidden layer, okay? It becomes the product. And then this quantity has to take the derivative respect to W1, and that will simply just give you the X. Now, on the other hand, if we study what is the gradient of my model function respect to the input variable X, and you see that because of multiplicativity structure, and in fact, the same term pops up because I have to take the derivative respect to the first hidden layer, and before I can take the gradient respect to X, right? So the same term pop up, and now this has to take the derivative respect to X, so I get the W1 transpose. So you see that these two derivatives actually share the common term, this piece and this piece are exactly the same. The only difference is in W and X. Now, by combining these two formulas together, I get the following statements, which is really essential. What this says is that the gradient in X can be written as what? As a product of this term multiplied this term, right? Here's just a simple bound. And now, what I can do now is here's a trivial statement, is that I can divide this by norm of X and multiply by the norm of X. But if you take a look now, the product of these two terms, the last two terms, what this actually gives me is, because this is corresponding to a vector, this corresponding to a vector, but if you take a look at the first formula, and this matrix is actually the outer product of these two vectors. So therefore, when I vectorize it, the norm of this term is in fact equal to the norm of this term multiplied together. So therefore, this term in fact is exactly the same as the W1 gradient. Okay. What you see here is that I can bound the gradient in X with a bound by the gradient in W1, as long as I'm willing to multiply this factor here. Now, this factor, you have W1 on the top and X at the bottom. So if I can assume that the W1 can never go too large, and also X is not too small, and then this ratio will be bounded. Okay. So now X2 not small, that can be controlled by normalizing my input data, right? So I can scale my input data so that they have all norm 1. This is a standard practice in neural network training. You do a little bit pre-processing on the data. So this is not hard to get. All right, so here in this slide, I essentially put, so the previous slide is really about one point X, right? Next slide, what I'm going to do is I'm going to average over all the possible different input data X. Recall my loss function is average over all the possible data point. So this is my empirical loss. And I'm in the overparameterization regime. And I assume my solutions in interpolating. And so therefore, for every input xi, fxi w star is equal to yi. Now, the flatness notation that people typically talk about in the literature is at least one way to formalize this, is you look at the Hessian of your loss function, and then you average over all its, or sum over its all eigenvalues. So in some sense, you take locally the Hessian and you calculate the trace of the Hessian. And that's one way to characterize how flat the Hessian is, how flat the landscape is at W. Now, if you do the calculation at the flatness of the W star, by explicitly writing down what would be the second order gradient of the loss function, and this will take this form, this long formula. But luckily, if my solution is interpolating as we have assumed, and we know that the model function is going to fit the data perfectly. So therefore, fxi w star minus y is exactly equal to 0. So the second term totally drop out. So the term that associated with the second order derivative, my model function drop out. So therefore, the only thing I have left is about the first order derivative of my model function. So if you clean up this a little bit, you'll see that this is actually the average of the two norm of my W gradient of my model function at my W star at all the training points averaged together. So flatness is really the average of the W2 the W gradient of my model function. Now, by taking the sum over all the possible data points, previously on the previous slide, I have take a look at the data points one by one. But if you take a look at all the data points, you get a similar formula where on the right-hand side, it involves the average over all the W1 gradient. And now, because W gradient is bounded by all gradients, right? Because total gradient W involves the gradient respect to the weights at all the possible layers. So if you only, but the statement that I have on the previous slide right here, you see that it only involves W1 gradient. So therefore, this can be upper bounded by the flatness. Okay. All right. So put into a theorem. So we have the following statement. This is just reiterating what I just explained it to you. I give you the proof before I state the theorem. So if my model function has this multiplicativity structure, so in the sense that, in fact, I only need the multiplicativity in the first layer, is that I take my input and multiply with W1 and then process it. And assume my data set is at the point x1 all the way to xn. And then so this is a shorthand notation for the average of the x gradient over my data. So you can think about it as over my empirical measure. So the L2 norm of the gradient x over the empirical measure is bounded by this factor, which I will talk about earlier. It's the W1 norm divided by the length of all the input x. So here I take the minimization because I want to get an upper bound. And then multiply by this flatness square root of the flatness. Okay, so you see that in this statement, the gradient appears, right? We care about the gradient of the model function. So that's why we call our work, the name I give to this topic called Sobolev regularization, because it's about the gradient. Now, so far I have been giving you the statement about the 2 norm, right? Here's a 2 norm, here's a 2 norm. But we can also lift this analysis. It gets slightly more complicated, but the essential idea is the same. We can lift this into higher norms. So suppose the norm P is equal to 2K, then we get a similar statement, not in terms of these 2 norms, but now in terms of the 2K norms. So as you will see that by making K slightly large will actually be useful when we try to prove a generalization bound. Okay. So before I tell you more about theorems, let me just give you some numerical evidence. So here we trained a 2 neural network. So on the left-hand side, we have the fully connected neural network. On the right-hand side, we have this kind of VGG network. Okay, so both networks are very commonly used, and these are in fact some early network examples. That involve that demonstrate this neural success of the neural network for vision tasks. So for the fully connected neural network, we train on the fashion minister data set. And for the VGG network, we train on the CFAR10 data set. Okay. Now, in both cases, we're going to compare these 2 quantities. One is a W derivative, and the other is X derivative. So we say that, well, you will recall that in the previous slide, so the statement is saying that the X derivative has to be bounded by the W derivative. And so therefore, GX should be bounded by GW. In fact, what you see is that empirically, there's actually an empirical linear relationship between GW and GX. So on the left-hand side, we have the fully connected neural network trained on the fashion minister data set. Here, different colors stand for different learning rate. So I'm turning my learning rate of my neural network training. And then I plot what is GW and GX as these 2 coordinates. And you see that GW and GX has this linear relationship. On the right-hand side, we have this VGG on the CFAR10 data set. And here we vary, the color coding shows that we vary the different batch size. So we train our neural network with different batch. And then again, here you roughly see a linear trend. And it bent down a little bit, but it's consistent with our theorem saying that the GX should be bounded by a function by linear relationship multiplied by GW. Okay. Now, I personally find that it's also useful to use the following picture to explain what is the really main idea about the theorem I just showed you. So here, let's consider the simple case where my input dimension X is equal to sorry. Here, let me consider the case where my input dimension x RD, where D is equal to 1. And we also consider the case where W belongs to RW, is that W is also equal to 1. Let's consider the simplest case where DW both are equal to 1. And this is the case where I can draw pictures because I can only do 2D, and the D plus W, in fact, is equal to 2. So because of multiplicative structure, my model function f will actually depend on the x multiplied by W. Okay? So because it's multiplied by W, so therefore, the function, in fact, my loss, because the loss is dependent on the model function. So therefore, the loss will actually be equal to, is going to be the same value on this constant curve of x times W, right? On this level set of x times W function, my loss is going to take the same value. Now, suppose I take a look at a point x. X is the data that I can change. It's a data set. And suppose W star is the parameters of the model function found by SGD. Now, what you see is that when W star is not too large, okay, what happens is that the smoothness, the oscillation of the function in the W direction, directly transferring into the oscillation in the X direction. Okay, because the level set, the distance between different level sets are comparable. On the other hand, if W star goes to the right, for example, I make the W star at this point more and more to the right, and then you will see that the oscillation in the W star direction become much more smooth, while the oscillation in the X direction become much more oscillatory. So in this case, any statement about the W derivative cannot be transferred into statement about the X derivative because you have this, the level sets get squeezed. But on the other hand, as I said, if the W star is not too large, you can directly transform the smoothness in W to the smoothness in X. So that's a key idea of the previous theorem. Now, in order to show generalization power, not only we need to care about the gradient at the point data point xi in our data set, we also need to care about the what happens in the neighborhood of x. So the reason is because my data xi are corresponding discrete points sampled from the data set. But if someone give you new data, I mean, these new data, testing data point will not be equal to any of the xi's. So the best you can hope for is that the testing data point, let me use a slightly different color, will be somewhere close to the one of these xi's. So therefore, in order to show the generalization power, we need to have an estimate on the gradient in x away from the grid over the data point xi. So what we do is that we extend it to a neighborhood. Now to do that, we need one technical assumption is what we call that the function, model function fxw satisfies this so-called C delta K condition. So the detail of the condition is not really not important, but what it really says is that if I change my W by a little bit, okay, if I change my model, the weight of my neural network a little bit, the model function should not, the gradient of the model function should not change too much, okay? So in fact, it can change quite a lot, in fact, but up to a constant factor. Okay, so we believe that this is a reasonable assumption because it's really saying that if I perturb my W a little bit and it remains bounded up to a constant factor. Okay, so once we have that, we have the following theorem. In this theorem, what we do is that instead of studying just at the data point, we study that delta neighborhood of my data point. So what I do here is that for every data point, I'm going to draw a neighborhood. And hopefully this neighborhood is going to collect, when you take the union of this neighborhood, it's going to, with high probability, it's going to cover the majority of my input data distribution. That will be an assumption which come in later. But this is essentially why do we need to extend it to a neighborhood? Okay, so then the theorem says is that if there exists, my pen. So okay, so what the theorem says that suppose my model function satisfies this technical condition which we assumed earlier, which is not so strong, right? And then there exists a neighborhood delta with delta radius such that the union of all these disks, within the union of all these disks, we also have this similar bound relationship between the x derivative and also the w derivative. Okay, in the sense that this relationship between x derivative and w derivative can be transferred into this union of these blue disks rather than just at the training data. Okay. So this is the part two, which came first. Is that, let me just summarize a little bit. So the key point is that by studying the multiplicative structure of the neural network, we showed that the landscaping X can be related to landscaping W. More precisely is that we can bound the gradient in X with a gradient in W. And and we can also study higher order. Sorry, we can study this relationship we can extend this relationship into the neighborhood of my training data. And also this flatness relationship I was talking about earlier can be extended from the 2 norm into higher order moments, the higher order norms.
Lexing, are you happy to take a question for this first part? We have one
Yes,
in the
yes, yeah, sure. You can, yeah, please go ahead.
Yeah, thank you very much. I have one question about the previous slide. This local smoothness condition, is that uniform? Do these constants C delta K depend on X, or are they uniform over the support of your measure of?
Right, good question. The way we stated is uniform. But for example, because we normalize the data, right? We assume the data is X norm is bounded. It does not get, we normalize it. In fact, I mean, we make it, okay, so you can think about it. After we normalize the data manifold itself will be a compact set. So therefore, and I mean, this statement, as long as it's true, hold point-wise in X, you can measure and make it uniform.
Well, yes, it will be compact if you are.
Yeah, if you normalize the data.
But I guess as your dimension grows, you are compact, but you're sort of less and less compact.
Right, the constant itself.
In a high dimensional space, it's not really compact. It is, but it loses its compactness properties as you go to infinity in the dimension.
Right. So your question would be that how the constant C maybe depend on the dimension, right? So here we, that's a good question. I think that here we assume the C is a constant that we didn't study the scaling. I mean, yeah, that's a good question.
I think we have, yeah, thank you. I think we have one other question actually from the virtual audience. Emmanuel Ström.
Yeah.
Yes. Hello. So I had just a question about this this weight W. So
yeah.
So you say, so it is found in a lot of these inequality expressions, and you say that assuming that it is bounded in some sense, we have this nice property that the gradient of the weights is bounds the gradient of X basically. And could you maybe comment on
for this?
Yeah, in practice, like this, how is this borne out in when you look at, because I know there have been some research on like I think some people call it spectral bias, where machine learning algorithms tend to kind of find the low frequencies first or whatever, low weights. Is this a reasonable assumption basically?
From the numerical results that, I mean, we did and many other neural network run in practice. So the W1 weights, you observe that W1 weights doesn't go to infinity. It actually remains quite bounded. So that's the numerical evidence. So theory-wise, we cannot prove, I mean, that W1 star will always be bounded. I mean, it's a result coming out of a neural network training, right? So after you training, you can, after training, you can check how big the W1 star is. But a priori, one cannot prove that. But for certain neural network, which are homogeneous neural network in the sense that, for example, use value activating function, there's this relationship which which essentially tells you that the weights between two adjacent layers, they satisfy a certain relationship. Now, that kind of relationship doesn't directly tells you that W1 can be bounded, so W1 can still go up, but that give you some confidence about, I mean, the W on all the neural networks weights cannot go to infinity as simultaneously. Now, I hope I answer your question. Is that in practice, yes, we observe that, and many other people observe that W1 is not bounded. Theoretically, to prove that this is always the case, or with high probability, is still an open question.
Yes, I think I got my answer. The only maybe so maybe you're mainly interested in kind of the limit case where you have very small norms, but I mean, even if W doesn't explode to infinity exactly, you could have problems if it's very, very large, right?
But you could have problem, I mean, W1 large, I agree, yes.
Okay.
But in that case, our theorem will not be very useful.
Yeah, okay.
Another question.
Sure.
Very briefly, the same slide, please, as before.
This one.
Yes, you said that that we normalize the training data anyway, and well, your training pairs are still in the original scale. So you have the original X eyes and Y eyes, and then you normalize the X eyes, and then, if I understand it correctly, you hope that your neural network will sort of figure out the scaling itself.
Okay, so in practice, for example, so I believe the most of the data set, for example, image. So for example, in this minutes data set, like the fashion minutes data set, and also CFAR10, all these images, if you take a look at the norm, and none of the images will have the norm like very, very small, go to 0. So in some sense, I mean, you're not studying images. For example, the grayscale value is very close to 0, right? Okay, so that's what I mean. So the data set is already pre-normalized in a sense, has a certain fixed, like it has a brightness of the picture bounded away from 0. So when you start training on it.
Sure, but maybe in some more realistic settings, when you have some medical images, maybe you have some images with really small norm, and you cannot pre-normalize them. If you actually collect something real, then you cannot decide on what the magnitude will be. And
I agree in this case, but overall, when you take a look at the medical images, I mean, I assume that it's not very close to a black image, right? That they will still have a part which is, for example, quite bright and white. But I agree with you that for specific, I mean, certain application, it makes sense to scale the data. Certain applications probably doesn't make sense to scale the data, and by rescaling the data, in fact, it might make your neural network's job to be more difficult.
So do you suggest if we have some real images and they are on very different scales, so something is very close to 0 and something is very bright, do you suggest that we sort of rescale them to be roughly on rescale the inputs so that they are roughly on the same scale? And
I
then
think this is
figure out the scaling itself.
And the neural network doesn't really need to figure out the scaling. For example, if you think about the regression function, you want to answer, now here I talk about regression, but if you want to talk about classification, so I want to tell whether the picture has a dog or cat in it. So after you rescale the images, and I mean, you don't have a very faint image, you don't have a very bright image, you have an image which more or less have the same energy. And the neural network could, in this case, I mean, I assume that it's not clear to me whether this makes the job of the neural network, the classification task, more difficult or less difficult.
If I have something like CT or MRI images, or shall I stop now?
Yeah, but maybe after the question we should continue.
Yeah, sorry. If you have something like CT or MRI images, and then your output, your Fourier coefficients or your sinogram, it will change actually depending on what you do with your input. But maybe we can postpone it to the end of the talk, because I'm sorry.
Yeah, it's okay, but I want to say that in some sense, or if you take the human visual system, right, in some sense you automatically adjust depending on the brightness of the image you see, and they might have same impact. I agree with you, but I think it's but I mean, as I said, I mean, human visual system already, if you look at the pictures in the night and look at the pictures in daylight, I mean, we will be able to recognize the two pictures, right? So in some sense, it's not, I don't think the adjustment of the input data itself will, even in the medical imaging case, would be, I mean, I'm not talking about the theorem, but I'm talking about whether in practice, whether the neural network will be trained on, whether trained on adjusted images will affect the overall performance dramatically, but we can take it offline.
Thank you.
Okay, now let's explain the second part, why the SGD makes the W derivative small. Now here the answer is that the flatness give you that. Sorry, the stability give you that. So now the stability for gradient descent and for SGD means very different things. So here I'm giving you a picture comparison of the gradient descent with the stochastic gradient descent. So the function, the loss function here, I choose very simple. It's just to be fx is equal to ax squared. Now, if you do the optimization on GD and with a certain learning rate eta, and you observe that, in fact, this is a very simple numerical analysis, ODE, or kind of analysis, a stability analysis, stiffness analysis, is that when the step size is less than 1/2a, so a is a coefficient in front of it, in front of my loss function. And then the gradient descent will just monotonically bring you to the minimizer, to the global minimum. But when, for example, the step size is gradient is greater than 1/a, and then starting from point even very close to the ground truth, and the stiffness, if the step size is too large, the problem becomes stiff. So therefore, I mean, you're going to blow to infinity. Now, within eta, within these two numbers, what happens that you will see an oscillating pattern. It's going to gradually still converge, but it got oscillate back and forth. So this is, the situation is very clear for GD. Now for SGD, in fact, is more complicated. The reason is because in the SGD, I assume that even though fx have this form is ax squared, but it's actually a linear combination of a bunch of functions. It's 1/n summation I from 1 to n of fix. Okay, so even though it's actually the average of a bunch of loss function, each of them is actually dependent on my different training data. So if, for example, if these fi functions are very close to each other, like what I show on the left-hand side, and then the same picture remains, if my eta is less than 1/a, it will either converge this way or it will bounce back and forth and converge. But on the other hand, if my loss function, these loss function fx, the two components, f1, f2, look very drastically different. So for example, f1 is has very large curvature, and f2 have a very small curvature. Then in this case, you will see that even with the learning rate, which less than 1/a or even much smaller, it's still possible for this SGD to go to infinity. The reason is because with half of the probability, it's going to touch this flat landscape. So therefore, even for big learning rate, you will converge. But half of the probability, you will touch this very peak landscape. Whenever you touch this peak landscape, what happens is that your learning rate criteria will be much sharper. So even for a small learning rate, you might also experience this blow up phenomenon. Okay, so the stability for SGD is typically much more strict compared to the gradient descent. Now here, by stability, what we mean by that is that when SGD finds a W star, our solution, and it finding a stable way, okay, in the sense that, I'll explain to you. Okay. Now, so stability means that I mean, yeah, okay. So the stability here, okay, no, sorry. So let's take a look at the gradient descent of my step, or the stochastic gradient descent. So here, within every gradient descent step, what we do is that we're going to choose a mini batch, which we denoted by Cassie. And then what we're going to do is that we're going to average over this mini batch, okay, of my gradient, and then multiply by the learning rate and update by WTI plus 1. Now, to show stability, in order to, I mean, for stability, I mean, the first thing you study is linear stability, right? You want to study at the ground truths that we find, how a stable perturbation, and how linear, what kind of condition the linear stability impose on us. So to study linear stability, what we need to do is that we can instead study this W tilde term, where the W tilde is equals to my W minus my W star, okay? And without loss of generality, I shifted W star to be 0, but I can rewrite the whole formula without making W star with this assumption, but it's just a formula looks like I have to put a minus W star everywhere. So let me just not do that. But when you study linear stability, really it's just take the gradient, do a perturbation of this nonlinear term which appear here. And once you do this is already a gradient. So if you do you do a perturbation, and this will actually give you the Hessian term, okay? So therefore, in the linear stability, we get the following relationship, and this is the condition of linear stability. Now we say that our W star is case order linear stable if and only if for fixed learning rate eta and for the mini batch size B, and the following statement is true. Okay, so here, I mean, we assume the learning rate doesn't go to 0, we fix the learning rate. And we also assume the batch size doesn't go to infinity and it's a fixed constant. And the linear stability essentially said that if I take the expectation, so now where's the randomness? The randomness in this mini batch, okay? So I take the expectation over my mini batch, then I study the case order moments of my neural network weight. It has to be bounded by a certain constant, multiply the case order moments of my initial weights uniform in T. Okay. Now, so here the K does not correspond to how many steps I run in my neural network. It's really a statement. The K could be, it's really a statement about the moments. I'm studying the moments of this random variable W star T. Now, by taking this expectation of this linearized dynamics, I get this relationship between the moments of the previous step and the moments of the next step, T+1, and the moments of the previous step. So from here, it's clear that in order to show that my linearized dynamics is stable, I mean, if my linearized dynamics is stable, then this matrix itself, which I denoted by T, has to be bounded by 1, has no. Okay, so here's just a simple statement saying that what I just described you, if, for example, my SGD and W finds the W star in a linear stable way, and its case order linear stable with a fixed learning rate and mini batch size, and then this T operator itself has to have a norm 1. Now, the nice thing is that if I use this statement, but I tested with the special perturbations of my W0. So in the sense that I study this linear statement, and then I perturb one neural network weights and see how does that tell me about my T. What it turns out is that if you plug in these perturbations, and a half a page of analysis will show that, in fact, linear stability implies this T norms to be bounded. And at these initial perturbations, it will give you the following statement. What it says is that, sorry, I made one mistake here. So at the W star, if you take a look at the W weights, and then you measure the 2K norms raised to the power 2K, and then you average over the data points, well, this will be bounded by the following quantity. So it's bounded by 2 times W, where W is the dimension of the neural network parameters, times 2 to the power B. So B is my mini batch size raised to the power K minus 1 over eta to the power K. So you see that this formula is useful when B is small, meaning that, or rather B is not too large. The mini batch size is not too large. And also when eta is large, okay? So, or meaning that eta is not too small. So this is consistent with the picture I gave you earlier, because what I want to do is that I want to show that that SGD dynamics being stable give me some useful information about my my function f. But if I take the full batch, right, then I will not see this individual function fi's. So that imposes less strict conditions on the stability. And also, if I take a really small learning rate, and then SGD also go back to gradient descent, so I will not be able to see the individual component of as well. So what this here is saying that if the mini batch size is small and also learning rate itself is moderate, then I will have a useful bound. Now with this result, we can combine the theorems in part 1 and part 2 together to get our main result. So recall in the part 2, what we showed is that the gradient f can be bounded by this term multiplied by the gradient in W, right? Now, the theorem that I just showed you says that the gradient of in W of my model function can be bounded by this extra term. So let me just copy it here. And if I take the case root, or rather two case root, it's corresponding to this term. Now, again, in order for this theorem to be useful, what we need is that we need the W1 to be not too large, and we need the X to be not too small. And we also need the W, W is large quantity, but we need the B to be not too small. So I'm a little bit confused. What do we, so we need, right. So, okay, so now it's okay. So this term is okay because eventually what we're gonna do is that we can make it K big. So therefore, even though this term could be large, but raised to the power 1/2K is gonna be small. The most important term is here. Is because B appears in the top and eta appears at the bottom. So therefore, for this theorem to be useful, we need the B to be small and the eta to be moderate. Okay, so we're talking about the stochastic gradient descent in the small mini batch size and also moderate learning rate case. So the previous theorem, the way I stated, is in terms of this is in the average sense because it's integrated over this neighborhood of my testing data. Now we can also lift it into the L1 estimate, sorry, L infinity estimate. In the case of the L infinity estimate, and in fact there's an extra term n pops up because I have to take the union bound over all my grid points. But as again, this term is going to be raised to the power 1/2K. So therefore, if my SGD is K order linear stable and the K itself is not a very small number, let's say 5 or 6 or even 10, and then this will be raised to a very small fraction power, and this term itself will not do any harm. So finally, let's use the theorem that we just proved to prove the generalization bound. Okay, so here I have, in order to prove generalization, and here I assume that I have a target function where the target function is the ground truth, and the yi is given by this target function, and the generalization error here previously my L is an empirical error, but when I talk about generalization, I have to take over all the possible input data distribution. So for all the possible data distribution, I care about what is the prediction of my model function minus the ground truth, and then I norm it square. In fact, there's a factor of 2 here, which is missing. Okay, but that's okay. Now, the theorem goes on the following. So here's all the assumptions that we made, and I claim that these assumptions are reasonable. So first is that my W star, the ground truth neural network weight that I find is, oh sorry, the limit of the SGD W star is a case order linearly stable, okay, with a fixed mini batch size and a fixed learning rate. And now I need this second technical condition, which I talked about earlier. In order to move away from the testing, the training data, I have to study the neighborhood of the training data. So I also assume the same assumption here. The third assumption is on the data set. So what it says is that with high probability, for a new point sampled from my data measure, it's going to lie in a neighborhood of my training data point. Okay, because this is why I need this the covering the union of the disk as your assumption that this is the assumption that the union of these small disks is roughly going to cover all the data. And finally, these are the assumptions on the target function. So I assume that the target function is bounded, and I assume the gradient of the target function is also bounded. Okay. Now, so once we have this assumption, we can prove the following statement. And in the following statement, the generalization error of my neural network that I obtained from SGD, and assume it's case order linear stable, can be bounded by 3 terms. The first term is what we have seen on the previous slide, plus 2 another terms. So these 2 terms, one is involved this gradient of the model function, and one is involved the model function value itself, multiplied by some small parameters. So therefore, in general, as long as the epsilon small, delta small, and we can show that the generalization error is also small. So let me give you a quick proof sketch about how to prove a statement like that. In fact, we have already done all the hard work. The only remaining thing we need to do is to just triangle inequality. Okay. Now, so what we want to do is that, let me just draw a picture. So what we want to do is that we have, let me use this color. So what we want is that we have this grid point. Sorry, not grid point. We have this training point, these xi's, and we now we have a disk, which the union of this disk is gonna cover more or less most of the data. Now, suppose you give me someone giving me another point xi here, x here. So first, what I'm gonna do is I'm gonna find the nearest training point. So this is the first step. So the triangle inequality is done. I transfer the difference in x of my model function and the target function in x by squeezing the xi term. So I'm gonna study the I'm gonna do triangle inequality based on these xi's. So in this triangle inequality, essentially I plug in this term and subtract this term, plug in that term, and also minus term, add a term. So right, and then these terms that cancel out, then I put an absolute value, I get an upper bound. But now if you take a look at the middle term, the second term is in fact is equal to 0, because this is the difference at my training data with the parameter W star. But because my W star is actually interpolating, so therefore this term is automatically equal to 0. Now, the last term is also do no harm, because this is a statement about my target function. And so therefore, in fact, this is really can be bounded by the gradient of the target function times the difference between xi and x. But as long as this gradient of the target function is bounded, so therefore this term is also small. Now, finally, let's take a look at the first term. Well, the first term is involved in my model function at my W star. But when x and xi are small, this term itself can be bounded by the gradient of f at some point between x and si. So let's call it x theta of my W star. At x theta, my W star. But now this x derivative bound, the L infinity bound, is what I proved here earlier, right? So therefore, this term is also under control, and that will give you this error term. Now, so you see that all 3 terms are either 0 or small. So therefore, by taking the sum, by adding them together, we prove the generalization error is small. Now, the same analysis can be also extended to the adversarial robustness case. So, but I claim that this is adversarial in this case almost the same as generalization, because what adversarial robustness means that if you perturb your input a little bit, you will not get the response, which is very different. So, but this is essentially the same theorem. It's a corollary of the previous theorem. All right. So to summarize, what I've talked about today is this one explanation about why the SGD generalized well. So the argument that we use is follow this standard one of explanation of the SGD finds a flat minimum, and then flat minimum give you a generalization bound. But we made it more precise. We identified that the flatness really means that the W gradient is small, and the generalization is related to the X gradient is small. And these are 2 different gradients, one with respect to the neural network weights, the other one with respect to the input data. So therefore, they're quite different. And to show the first step, why SGD finds small gradient in W, here we use a stability. Okay. And now, in some and also this, I want to emphasize this is a condition statement. What this says is that if SGD finds a solution, interpolating solution, which is linear stable, then this is true. But it's also possible that SGD would be not able to, for fixed Bennett batch size and for fixed learning rate, it will not be able to identify a stable set of neural network weights. That's possible. It's possible that the SGD is hopping between different two solutions, right? That's possible. So therefore, this is a conditional statement. For the second part, the key structure we use is the multiplicativity structure of the neural network. And you recall that by using multiplicativity, we can transfer the bound on the W derivative to the bound on the X derivative. Now, there are a lot of interesting questions remains. So for example, what if my W star is not an interpolating solution? What's going to happen? So we use the key step that fxi W star is equals to my yi, so that I can get rid of the second order derivative, the Hessian of my model function, right? But if I cannot do that, then the proof have to be, I don't know how to prove it. Okay, that's one open question. And the second is that, what if the loss is not a square loss? And that's, I believe, is a minor issue because I wouldn't say it's a minor issue, but it's probably, our analysis could also be, I think it could be extended to that. And finally, I think it's also very relevant is that, what if the optimization algorithm you use is not SGD? Well, SGD is one of the most popular algorithms used, but by no means the only one. There are algorithms like ADAM and also many other versions of algorithms used in training neural network. And can the analysis also be extended to these algorithms? And finally, here in our proof, as you see, the multiplicativity structure is actually only using the first layer. It's not using every layer. But in the true neural network, you have this multiplicativity structure in every layer. Can we somehow leverage this extra structure to get a better bounds and to say more about this SGD implicit regularization? Okay. So I'd like to thank you for your attention, and this work is based on this paper, which is going to appear in NIPS in this year. So the original title is a bit different. It's the title of this talk called Sobolev regularization, but the reviewer asked us to change the title, so the new title will be this one. Okay, thank you.
Yeah, thank you, Lexi. Thank you very much. That was very, very interesting talk. Are there questions in the audience that haven't been asked?
All your analysis is based on.
Oh, sorry, I can't hear you very well.
So all your analysis is based on linear transformation followed by ReLUs, right? Or by nonlinear activation functions. Is that correct?
Yes, no, it's not a linear activation function. The activation function is not linear. It could be ReLU. Yeah, but it's linear transformation, and then you feed it to ReLU. It doesn't need to be ReLU. It's but yeah, ReLU is a good example.
So my question is, does your analysis basically hold? Just becomes probably a bit more complicated if you introduce biases.
Well, I mean, the biases could be handled. For example, one way to include the bias is that you append a constant one. You increase the dimension of the input by one and add a one to that.
Yeah, but you have to do it in every layer, right?
You have to do it in every layer, yes. So, right. Yeah, I mean, it could become more complicated. That's a good question. Yeah. Hello. Can you still hear me?
Yeah.
Yes.
Yeah. Okay. Yeah. So I think yes, I have to go back to the paper and then take a look at what are the details. But
I actually think it should be okay.
Yeah.
Because you can do this transformation, then the only problem is that all your xi variables have the same input in that additional dimension, which is 1. But I don't think it's a problem.
But then you need an input on every layer, right? An additional 1 as an input on every layer.
Yeah, but I think you see, I mean, in the later layers, we didn't really use much, right? In fact, all the analysis based on the first layer, right? The multiplicative structure in the first layer. So I think the proof will go through, but I can't promise at this point. But I need to take it. But I'm pretty confident it will go through.
Thank you.
I may have a question, if I may.
Yes.
Because it probably refers a little bit to the last point you made, because so you have this multiplicative structure of your feed-forward neural network. I think I have probably 2 questions about this. So the first one, or the obvious one, would be, say, we go to something more like a ResNet structure, or something with skip connections.
Mm-hmm.
Do you think, like, you have an idea of how you could basically translate the theory to more general cases? And do you think, because often people argue that with skip connections, the training gets easier. There were even papers which were then arguing that the objective function seems to become sort of more convex. And I was wondering if then someone would also see maybe in return also maybe flatter, more flatness in some ways when, let's say, ResNets would be easier to train. Do you think there's an argument for this that could be made, or?
Yeah, I mean, for most of the ResNet I know, right? I mean, I think given the input data, what you do first is that you have to go through some kind of like linear transformation. It's like a fully connected layer to transfer things to the feature, what we call feature dimension, right? And then feature space. And then on top of the feature space, you do this ResNet. So therefore, in most of the ResNet, you will have the first layer that I was talking about here, this multiplicative layer. So, but because our analysis is only using the multiplicative relationship in the first layer, which does exist in ResNet. So I think the proof will include the ResNet. Okay, most of the ResNet. But now you bring the important question is that how the later layers in that ResNet and change the landscape, right? It doesn't make the loss function more convex. So this will have an impact on the stability. So right, because in the stability analysis, it's a conditional statement, as I mentioned, is that we assume that SGD converge in this k-linear stable sense to W star. By changing the landscape, that might affect this convergence. So that might affect what would be the beta and B and the eta that achieve this k-stable convergence. So it will be a more refined analysis, which I don't think we can do at this point, but it's certainly an interesting future direction.
Yeah, and maybe along similar lines what you just said. Also, obviously you're right. I should have thought about that. You basically just use the first sort of input layer for the initial estimates. But so the next thing that would also be, so let's say if you have a deeper network, would the argument be similar that let's say, or I'm not sure it would be similar, but let's say if you often people obviously argue that when they have very deep networks with more sort of expressive power, they get better results. Would you then also expect that this would sort of maybe go into the constants in your sort of SGD analysis? Let's say if a deeper network makes or would basically in practice yield better results. Would you then expect that that would also be reflected in the constants in this particular in the SGD analysis? Because obviously it doesn't go into the estimates of your first part, because it should be they should be completely not affected by how many layers you use, right?
Right. I mean, our analysis doesn't answer this question. It's just assume that whatever landscapes that you give me, and assume that you train the SGD successfully, right? You train the 2W star with a fixed learning rate, eta, and mini batch size. And then our theorem is take over from that point. So now by making it deeper and also make it more expressive and also use like a ResNet, the training might get easier. And so these are not the questions that we are addressing in this paper, but as I said, certainly, I mean, it would be nice to see that for different architectures and for what the beta and for what the eta, you will get this k-linear stability. That itself is an interesting question. But in some sense, this is like studying the part as a step, like where our analysis is based on.
Yeah, thank you. Thank you very much. Do we have more questions from the audience or
One,
the virtual? Yeah,
one short one.
no worries. We have time.
So it's a rather simple, maybe trivial question. Your theorems assume that the function f is differentiable in x and w. But then if you use something like a ReLU, you are not differentiable anymore. How does that fit together? So does it not apply to ReLU networks then?
No, in fact, I mean, here, I mean, I only take one derivative, right? And then, so therefore, for example, for ReLU, you can still take one derivative. And also, so I think that's okay. So, so in our analysis, we didn't use the second order gradient with respect to the model function. We didn't use the second order gradient with respect to W. So I think for ReLU, that's okay. But now if you have a disjoint, discontinuous activation function, then the analysis breaks down.
Okay, thank you.
Sure.
Yeah, thank you. I think, so I don't see any further questions being raised in the room, and I also don't see anything in the chat. Then I would say let's thank Lexing again very much.
Okay, yeah, thanks a lot.
A series of 3 very nice talks, and yeah, we'll conclude here. If there are obviously further questions or further discussions, I guess they can be taken sort of offline or via email, I reckon. And
yeah,
yeah,
certainly. Yeah, if anyone has a questions, please send me an email. Thank you.
Perfect. Yeah, thank you, Robert. Thank you again. Thank you very much. And bye.
Thank you.
Bye. Take care.